In the previous lecture, we had motivated this very important relationship between entropy and the second law of thermodynamics, that delta S for the universe is always bigger than or equal to 0 in all processes. And in order to motivate that equation, I had done some examples. Most of those examples had to do with exchanging heat between solids and liquids, and solids or liquids changing phase. And the thing that we had left out of those discussions was how do I handle gases? And that's the purpose of this lecture, is to talk about the entropy change in an ideal gas. So if I want to know how much the entropy changes in an ideal gas in some process, how do I do that? That's the purpose of this lecture. And again, to start, I'm just going to do some examples. So the first one, let's think about a reversible isothermal process. So hopefully you remember what an isothermal process looks like on an ideal gas. If I've got a container full of gas, maybe the gas is compressed by some masses on top of the piston, like we see in that figure, and I start removing the masses one at a time, slowly, and then the gas will expand slowly because the pressure is being reduced, the volume is increasing, and then heat will flow in to the gas from the surroundings in order to keep the temperature constant. And on the left, you see the PV diagram of that process. So how do I calculate the entropy change of the gas in this process? Delta S for the gas. Well, delta S, like always, is the integral of ds. So delta S is a finite change. ds is an infinitesimal change, and to get the finite change, I just add up all of the infinitesimal change. And then we can put in here the definition, dq reversible divided by t. So in the last lecture, I was a little sloppy. I wasn't writing down this reversible. So that's important, and that's really going to be kind of the key point of this lecture, is why we need to have that there. So remember, this is heat added in a reversible process. To the gas divided by the temperature of the gas. And now we've seen this many times. So in this case, it's an isothermal process. So that means the temperature is constant. So this temperature can come outside of the integral. And so then I get 1 over t, integral dq reversible. And so the integral of dq is just the total heat added in the reversible process divided by t. So delta S for the gas is q divided by t. So that's one formula that you could use, but maybe you want to know what is the entropy change in terms of the initial volume and the final volume. For that, I need to remember that it's an isothermal process, which means that delta U is equal to 0. Let's go back to the first law. And the first law tells us that delta U is equal to the heat added minus the work done. And so if delta U is 0, then the heat added is equal to the work done. So I get the work done, or the heat added in the reversible process, is equal to the work done in the reversible process. And we know the formula for the work done in a reversible isothermal process. We worked it out many weeks ago. Nm are the temperature times the natural log of Vf over Vi. So this is going to be Vi, and this is Vf. So I know the heat added is equal to the work done, and then this NMRT natural log Vf over Vi. Where does that come from? In case you forgot, this comes from this formula, right? Integral of P times dV from Vi to Vf, and then substituting in the ideal gas law in for P. So finally, we can put everything together. We've got delta S for the gas is Q reversible divided by the T. And then Q reversible is NMRT natural log Vf over Vi. So I'm going to combine now this equation and this equation, and I'll get my final formula for delta S for the gas in an isothermal process. It's just going to be this same formula that we have down here for Q, but divided by T. So it's going to be Nm R natural log Vf over Vi. So there's our formula for the entropy change of the gas in an isothermal process. And it makes sense because if Vf is bigger than Vi, the thing inside of the natural log is bigger than 1, delta S will be positive, and that's because heat is being added to the gas, so the entropy of the gas will go up. If Vf is smaller than Vi, that means the gas is being compressed, and heat will flow out of the gas. The thing inside of the natural log is less than 1, and so delta S for the gas will be negative. Okay. So here's a little concept test having to do with the previous concept of the entropy change in an isothermal process. Two reversible processes are shown, so one going from 1 to 2 or from 1 to 3, and it's an ideal gas. And assuming the gas is the same number of moles and the containers are identical, the question is, how does the entropy in state 2 compare to the entropy of the gas in state 3? So is the entropy in state 2 bigger, smaller, or equal to the entropy in state 3? One of these is reversible isothermal, or one of these is reversible adiabatic. So I'm not going to answer this question. I'm going to give you hints in the right direction. The first one is first hint I'll give you is I'm asking you about how does the entropy of the gas in both of these states change, right? Entropy of the gas, entropy of the gas. Suppose, just to avoid some confusion or to make it a little bit, to illustrate a tricky point, if I had asked you what was delta S for the universe in each case, what would be the answer? If you don't know right away, pause the video, take a moment to think about it. Okay, so I will answer that question. Delta universe S universe in each case would be equal to 0 because they're both reversible processes. So that was what the topic from last lecture, right? That if the process is reversible, the entropy change of the universe would be 0. But that doesn't mean the entropy change of the gas is 0 necessarily, right? Remember last lecture, I could increase the entropy of the universe of one part of the universe if I decrease the entropy of another part of the universe somewhere else, and then I would end up with a reversible process where delta S universe was 0 in each case. So I'm not asking that question about the delta S for the universe, I'm asking delta S for the gas. And that could be positive or negative or 0 in each of these cases. Okay. And one more hint I will give you is go back to this definition, delta S for the gas is equal to the integral dq ReV divided by T. And see if that can help you answer the question A, B, or C.